In this video, we're going to take a look at some trig equations which are quadratic in form. This means that these equations will look a lot like quadratic equations, except instead of a variable, there'll be a trig function which serves that purpose. An example of such an equation is this one here, where we want to solve the equation 2 sine squared of theta plus 3 sine theta minus 1 equals 2 sine theta. We can rearrange this by moving the 2 sine theta to the left side by subtracting it, and we obtain an equation of the form 2 sine squared theta plus sine theta, because we have 3 and are subtracting 2, minus 1 equals 0. And now this equation looks like a quadratic equation, except that the role of the variable is played by the function sine theta instead of a variable itself. If we don't like thinking about this, what we can always do is make a quick substitution, maybe u as an example of a variable that we could replace sine theta with. And if we did this, we see that we get 2u squared plus u minus 1 equal to 0. And this is the same equation, except using a variable u in place of sine theta. Now this is exactly a quadratic equation, and we can factor this. In this case, 2u minus 1 times u plus 1. Of course, if we could not factor this, we could have always used the quadratic formula or completing the square, but most of the time these will factor nicely. And so here we set each of these factors equal to 0, and we can then solve for u in each case. So the first one here, we add 1 to get 2u equal 1, and then u equal 1/2. And the second one, we subtract 1 to get u equal to negative 1. Now, we might quickly say that the solutions to our equation are then 1/2 and negative 1, but these would be the values for u, where we want the values of theta. So now, resubstituting, we've boiled this down to sine of theta equals 1/2 and sine of theta equals negative 1. These are each basic trig equations that we can then solve. And so here we know for sine theta equals 1/2, we know we get theta is pi over 6, as well as theta being 5 pi over 6. These are our two angles between 0 and 2 pi, whose sine is 1/2. And we can add the multiple of our period, 2 pi k, to each of these to obtain all of our solutions of each particular form. And for our second one here, sine of theta equals negative 1, we only get one possible angle here. This is between 0 and 2 pi. Our only solution is 3 pi over 2. If you need a quick refresher about that one, we can just remember the unit circle, and that the sine function is the y-coordinate of our point. And so here we're looking for a point on the circle where the y-coordinate is negative 1, and there's only one such point down here at the bottom, and that corresponds to a 3 pi over 2 radian angle. And so then we can also add 2 pi k to this particular angle, and that is since that is our only solution between 0 and 2 pi, we end up with 3 sets of equations here: pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, and 3 pi over 2 plus 2 pi k, and k here represents any integer. So these are all solutions to the equation at the top of the screen. If you'd like to practice with a similar example, try to solve the 2 times cosine squared of x minus 5 cosine x equals negative 3. The solution and a couple hints about the procedure will appear in just a few seconds. So if you move the negative 3 to the left-hand side and factor, we should ultimately end up with the equations cosine x equals 3/2 and cosine x equals 1. Cosine x equals 1 has a single solution between 0 and 2 pi, and that is x equals 0. There we're looking for a point on the unit circle where the x-coordinate of the point is equal to 1, and there's only one such point, the point on the right-hand side of the circle. And our first equation was cosine x equals 3/2. Notice that there is no solution to this particular equation because the cosine of any angle x must always lie between -1 and 1. Those should both say less than or equal to because both 1 and -1 are allowed. But in this case, we know that 3/2 does not lie in that appropriate range, and therefore cosine x equals 3/2 has no solution. And so our only solution, our only specific solution is 0, and then adding all multiples of the period 2 pi to that gives just 2 pi k for k any integer. In this example, we want to solve the equation 2 sine squared theta plus cosine theta equals 1, and we only want to find the solutions here that are between 0 and 2 pi. This means that we don't have to add multiples of the period 2 pi at the end, but otherwise we have to do all of the other steps of the problem. This looks somewhat like the previous examples in that we have a trig function squared and a trig function and a constant. However, the difference here is that this example has both sine theta and cosine theta. And so in order to factor this, like we did in previous examples, we actually need to have the same trig function, either sine or cosine, throughout the entire equation. Luckily here, since we have sine squared of theta involved, we can use the fact that sine squared of theta is 1 minus the cosine squared of theta. We can then substitute that in for 2 times the sine squared of theta, and we will obtain an equation that involves cosine of theta as well as cosine squared of theta, and then we'll be able to factor and proceed as before. So when we do that here, we'll end up with 2 times the quantity 1 minus cosine squared theta plus cosine theta. And maybe I'll go ahead and subtract the 1 to the other side. At some point I'm going to have to do that, so we'll go ahead and do that now. And here we'll distribute the 2, so we get 2 minus 2 cosine squared theta plus cosine theta minus 1 equals 0. We have then, we can combine the constant. The 2 minus 1 will become a positive 1. So we have minus 2 cosine squared theta plus cosine theta plus 1 when the constants are combined. And when factoring, I personally find it easier if the coefficient in our leading term was positive. And so I'm going to just multiply both sides by a -1, and we'll obtain 2 cosine squared theta plus cosine theta. Sorry, that should be minus cosine theta minus 1, and that'll be equal to 0. If we wanted, we could substitute in a new variable for cosine theta here. We can also just factor this as if cosine theta was a variable. And so in order to do that, we see that this would factor as 2 cosine theta plus 1 multiplied by cosine theta minus 1. So this would be the factorization of our equation. And now we're going to set each of these factors equal to 0 and solve for cosine theta, and then find our angles theta in each case. So setting each of these factors equal to 0, we get that 2 cosine theta is equal to -1, and therefore cosine theta is equal to -1/2. And the second equation becomes cosine theta equals +1. And so we now can analyze each of these two basic trig equations separately. The first one, we want all values where cosine is -1/2. And this would be both in the second and the third quadrants where the cosine function is negative. And we know cosine of pi over 3 is 1/2. And so we're going to be looking for an equation, or the angle in quadrant 2 and 3, whose reference angle is pi over 3. So this would be 2 pi over 3 in quadrant 2 and 4 pi over 3 in quadrant 3. And so these are our two angles whose cosine is negative 1/2. For cosine of theta equal 1, we want theta to be equal to 0. This would be the only point on the unit circle between 0 and 2 pi where our cosine is, or our x value of the point is equal to 0. And so we end up with three solutions because remember, we only wanted the solutions that were between 0 and 2 pi, and 2 pi was not included in that, and so is not included here. And so we have a solution. We have our solutions of 2 pi over 3, 4 pi over 3, and 0. If you'd like an additional example to practice, try to solve 3 sine x plus 3 equals 2 cosine squared x, where x is between 0 and 2 pi. The correct solutions will appear in just a moment. So when the cosine squared of x is replaced by 1 minus sine squared of x, and the equation is simplified and factored, the resulting pair of basic trig equations should be sine x equals negative 1/2, which has solutions of 7 pi over 6 and 11 pi over 6 between 0 and 2 pi, and the equation sine x equals negative 1, which has the solution of 3 pi over 2. And so our three solutions to this equation should be 7 pi over 6, 11 pi over 6, and 3 pi over 2.